an exam. Quite a lot of you here today, so that should be okay. Now, the exam period is late. Starts 23rd of May and ends 11th of June. So sometimes there we have to take the exam. So now it's the question, who's going to be here, when? So let's try to see if we can locate a date. I should have warned you in advance, of course, that you have your you should have your dates with you, but let's at least try to come up with some suggestions. I'll post our suggestion on the homepage, and then those of you who are not here will then have a possibility of come with another, say, anti-argument or something, before I send it into the exam office as a suggestion. Now remember, it's only a suggestion, so we can't guarantee that we actually will get this this time, but at least we can try. So I just go through the possible dates that we have, and just raise your arm if you are busy, if you are going away, or if you are not present, or if you have another exam either the same day or very close up to it. That's also not so funny. So I start Monday the 23rd. Anybody of you is away or is not suitable? So Monday the 23rd is okay for everybody? Well, then it's not a problem. That was nice. How about 24th? There's one. And 25. Yeah, 26. You're going away?
No, two exams.
Okay. And also 27th? 27th is okay? Nobody else? So we have 23, 27, Saturday also an option, 28th, that's also okay. Sunday not so actual, no, Monday the 30th, 30th is okay, and 31, and the 1st, and the 2nd, and the 3rd, and the 4th, and the 5th. Not the 5th, sorry. That's the 6th. That's okay. And the 7th, and the 8th, and the 9th. And the 10th is okay, and the 11th. Okay, so that was actually quite a lot. Nice, nice, nice. Because, I mean, if you have another exam, then they will automatically forbid us to take the exam at the same time, of course. But that's the only thing they will see. So if you're going away on a conference, or I had one year when a guy had to go to a honeymoon. Okay, we fixed it. So that's also an option. But now there was plenty of spaces. I'll put out the suggestions, the possibilities, and then send them to the exam office in a week or so. So hopefully this should be okay. Good, good. Very good. We were talking about multigrid the last time, and we had gotten as far as talking about these V-cycles, and frankly at this level you already know, I would say, sufficient to be able to use a multi-grid method. When you start up an advanced solver and you say, he has the possibility to use multi-grid, so you choose that. It's normally the fastest one. And then the code will ask you, what kind of cycles should we use? V cycles, W cycles, mu cycles. And then he will also ask, what should new 1 be? What should new 2 be? And that's the number of iterations, new 1 on the way down, new 2 on the way up again. So there you now know you should pick quite small numbers, 1, 2, or 3, and play around with it a little bit. But that's normally the amount of input you will have in a multi-grid code. We have one thing else that we have to discuss, when to stop. So the stopping criteria, we will address a little later. Yeah, so we went through these different schemes. So interesting, full multi-grid, recursive definitions. We talked about the performance, and this is a very attractive thing about multi-grid. It doesn't need much memory at all. If you look at the storage required, you need to store all the unknowns on all meshes, but the sub-meshes, they will hardly take any space compared to the finest mesh anyway, especially when you go to 3D. You will have 1 plus 1 over 8 plus 1 over 8 squared and so on. So the subgrids, they hardly take any space at all. So it's a very efficient method when it comes to memory. And when you think it's also very efficient when it comes to speed, then this sounds really attractive. So multi-grid is definitely something you should think about using. Orsat here has created some examples for us, so he calculates actually the number of cells needed here. And he went only to a 2D problem. If you go to a 3D, you will get quite fast a tremendous amount of cells if you want many levels, of course. Work unit. This is something you should know about. A work unit, that is the price you pay for one iteration on the finest level. Now we use this sort of as a measurement when you want to check how many operations is needed to perform, say, one single V cycle. Well, on the fine level, one iteration will be one work unit. On the sub level, the next coarse grid, if it's a one-dimensional case, you only need half the number of operations, so that's 1/2 work unit, and so on. So in that way, we can sort of accumulate the work needed to, say, perform one single V cycle, for comparison with other methods. So the costs sort of have the same recipe as the storage. So here, the number of dimensions you have. So 1 plus 1/2 plus 1/4 and so on, if it's a 1D case. Yeah, I won't go through the details here with the anode truncation level and also some optimum parameters. So this you can read if you are interested, but I won't bug you with this. The cost of one V-cycle, well, as we have discussed already, you use then the work units. You have to specify new 1, new 2, number of iterations on the way down, coarser and coarser meshes, number of iterations on the way up again. Then it's sort of easily to accumulate all work needed to perform one single V-cycle. then it's a question, how many V-cycles do you need then before you're satisfied? A little bit up to you, of course. And it can be shown that the cost of converging within one single V-cycles will be the number of unknowns times ln to n, which then is comparable with a fast Poisson solver. So using Fourier, it's a very fast solver. So it's definitely comparable with any other fast solver. And it's possible here actually to find that the multigrid is of order the amount of unknowns you have, meaning order n with a problem with n unknown. And that's definitely the fastest method there is. In practice, you won't achieve this unless you have a very nice equation, linear Laplace Poisson equation, and your problem is rectangular, square. We'll see examples of this later. But yes, as an optimum case, it's possible to achieve this order n operations. Within this material you have been given is a couple of problems. It's a one-dimensional problem and the same, but then in 2D. So it's a very cute little problem, and as you should see from this original equation, this will then result in just a pure three-diagonal coefficient matrix, which easily can be solved directly, of course. So this is just a model problem. The physics behind it, you will have the pressure gradient balances the double derivative. So here you will have a Poisson flow between two parallel plates with these boundary conditions. So the solution was a parabola, which then is from laminar flow, very easy problem. He has created or supplied you that with two different codes. One is a V duct, another is an S duct. So the V duct starts directly on the V cycle. You start on the finest mesh. The S duct starts on the coarsest mesh and go one way up. And from then on continuing with ordinary V cycles, just to see if this one improves performance. So you have been given subroutines listing in appendix. And here we are getting into the troubling world of programming this if you want to make a program yourself. I won't recommend it. I did it, and it's a crazy way to waste time, but be my guest. So the way it has been programmed here, it's a sort of one vector storage of all your unknowns, regardless of the mesh you are in. So you have one huge vector where you put all your unknowns inside, meaning you have to have a lot of bookkeeping to find out which mesh are you on. So you need a pointer inside that long vector to find your unknown at the appropriate mesh. So little tricky. This to make a code more, say, generic. If you have just one single case, you know the finest mesh, say both x and y direction, you wouldn't program it like this. Then you would have created separate matrices for each mesh. But in a generic code, where you can have sort of any geometry, then this will be the classical way to do the programming. To give you an idea, if you want to program this, So one grid function set up all the meshes. You have a routine putting your left and right hand side of the equation system on each grids. Put 0 inside them. The key, that should then be sort of finding the pointers inside each mesh. Residual calculations. If you can recall from the V cycle, on one level you fight the residual equations on every stage. So you have to find the residual and then immediately push it down to a coarser mesh. So this residual calculation finds the residual and then push it down to a coarser mesh, and here they have chosen injection. This could also be a question in a subroutine or in a CFD code. I want to use multigrid, and then also the code can ask you what kind of injection should you use. Should you have full weighting here, halfway weighting, how you go from a fine mesh to a coarser mesh. That can also be a question in CFD code. And then going the other way also, we also could have some question, how do we do this? Interpolation. Prolongation from the coarse mesh to the fine. Here, just linear interpolation. And then the relaxation. How do you perform one single iteration? Also a question that could be made in the CFD code if you choose as multigrid. And here it's simple Gauss-Seidel. It's the easiest one to program. If you want Jacobi, remember, you're going to need additional storage. You have other choices here as well, especially when we go to 2 and 3D. More of that later. So there you have the two different programs. V-duct, simple V-cycles all the time. S-duct, just once you start on the coarse grid as an initial, or to find a better initial field on the fine mesh first. And to have something to compare with, you solve the same problem first. Now using the SOR, successive over-relaxation, with close to an optimum omega, the most efficient one. And here, the work unit, that will just be simple iterations. Now we are just on the fine mesh, nothing to do with multigrid, this is just for comparison. And here finding the epsilon, we know the analytical solution, so no problem finding an adduct. And I think here the adduct is the norm 2, if I recall correctly. So you see 20, 30, 40, 50 iterations. After 50, the adduct is down to 10 to the power of minus 4. For the multigrid, it brings out here the grid levels. So 5 should then be on the finest mesh. So this is from the V-duct code, starting with the V-cycles directly. And you see the adduct can only be calculated on the fine mesh. On these sub-meshes, you are working with the residual equation. So it's really not possible there to find an adduct with real physics in it. So that's sort of pure math inside the sub-meshes, the residual equation. And now, if you look at the work units listed over here, so we start on the way down. You see we have only one iterations one relaxation, one sweep on each level. So the work unit, final mesh, only one, and then 1/2 added into it. That's the sum, the first course mesh, and then add 1/4 and so on, all the way down. When we go up again, we use 2 relaxations on each level. And then, having done 1 cycle, we are at this arrow level with close to 6 iterations on the finest mesh. So this is how you should interpret these work units. The arrow, 10 to the power -2, not too impressive. If you go to the second V-cycle, well, 10 to the power -3 after 11.5 iteration. At least much more efficient than the SOR. Say 3 to the power -3. How much did he need it to get there? 10 to the power -3, you are here, 30 iterations. So we only used 1/3. Now remember, this is a one-dimensional problem, and it's not that many cells either. So the efficiency here will increase tremendously if you go to a real 3D case. Here's just the input file for this case. So just total number of grids, 5, which then defined how many cells you have on the finest mesh automatically. Using the S-duct, then you start on the coarsest mesh, just to try to find cheap, fast, and good initial solution on the fine mesh. So here on the way up, 2 iterations on each level, and then on the fine mesh you start with an arrow which already is quite small actually. So say call it a lucky choice here. And then from then on we just use ordinary V-cycles. So the first V-cycle didn't improve that much. So here is a question, maybe 1 iterations on the way down is a little few. Maybe we should have tried 2. But after the second V-cycle, now we are talking efficiency. 10 to the power of -5 with 15.5 iterations. So yes, it's very, very efficient indeed. And here the SOR had to use 50 roughly to get to the same accuracy level. Second model problem. The same physics, just a double derivative equal to -1, but now in 2D. So again, you have an analytical solution for this one. So you can do exactly the same. Now with the programs VDuct2 and SDuct2. And again, to have something to compare with, running an optimum successive overrelaxation, omega pretty close to 2. You need, say, 80 iterations to get the arrow down to 10 to the power of -3. Now with multigrid, first the storage, a little messy. Here you start with the V-duct, dropping directly into V-cycles. Again, 1 iterations on the way down, and then 2 on the way up again. And here we have 6 mesh levels. After 1 V-cycle, and to the power of -2, another V-cycle, the arrow 10 to the power of -3. Now we are talking 8 iterations instead of 80. So So you go into 2D, the factor is then 10. Very efficient indeed. So here the S-duct starting on the coarse mesh just to get a good initial field. Should be a little bit more efficient, not that much difference actually. Yeah, roughly 10 units there as well. Again, the improvement of one V cycle here is not that good, I would say. You should be able to reduce the anode by an order 10 in one V cycle. Of course, then you need a lot of, or more than just one iterations on the way down. But still, decent performance. It will be sort of a balance you have to find yourself. Should you iterate a lot, many times on the way down and on the way up again, versus is it cheaper just to take many V cycles? So there you can play around with the input data. Here we are touching into the world of numerics, and this can be very heavy indeed. So the numerical theory behind multigrid, that is, if you really want to get a headache, you can start looking into this. It's very, very complex indeed. So this is just a little taste of it. You can define something called here a convergence factor to see how well they perform, and then out of these parameters on each level, you can then use them to decide where should I go next. Should I stay on this level? Should I go to a finer mesh? Should I go to a coarser mesh? So it's possible to play around with your V cycles to be more say optimum. So you can sort of jump around between the meshes to find the most efficient way to solve the problem. But again, as I said before, if you start playing around inside that, you will spend more CPU finding the optimum way than actually solving the problem. So for us as engineers, we just want to solve it. You will just set up, use 10 V cycles, finished. Or if you have the possibility of finding a good stopping criteria. When should we stop? The danger here when you start playing around with this method is that you can fairly easily find the solution down to machine accuracy. You solve your algebraic equation system with an anode 10 to the power of minus 16 or something. But why should you? So it's a question there. Well, you can have a look at these definitions if you like, but again, a waste of time, I would say. Because what you are actually interested in will of course be the fine level solution. There you have the physics, and here you should then interpret, is the solution accurately enough? And if you can make this anode 10 to the power of 16, yes, you can do that. But remember the origin of your equation system. That's from a discrete equation system. Typically here, second order accurate. So that means you have an anode before you begin, which in this case will be delta x squared, of order delta x squared. So when your anode is below that, there's no point in continuing. You don't gain anything. So definitely stop before you reach the machine accuracy. That will be silly. Yep.
Can you quantify the original discretization error? You know the order, but you don't know the number.
Yeah, that's a good question. So when to stop? If you can recall the Sola algorithm, first step, that was calculate U star using the old pressure time level. This U star, that was the tentative velocity field, which then was in general wrong, doesn't satisfy the continuity equation. Second step, you have to solve a Poisson equation, which then looks something like this. Double derivative of the pressure difference between the new and the old pressure. And on the right hand side we have something here, a delta T and a density or something, multiplied with the divergence of this tentative velocity field. Here you have to pay the price in CPU. This is an elliptic equation. This is what's going to take time to solve. Calculating U star, that's just one sweep over the entire area and then you have it explicitly, so no problem there. And also the last step, you update the velocity to the new one using, and then you had to use U star and the just newly found pressure. Also step 3, it doesn't take time at all, so no problem there. So the question is, solving this one, when should we stop? In Sola we discretized that one using then second order schemes. So this equation, the algebraic equation we get, will be then of accuracy h squared. H being delta x, delta y. So we know the accuracy of this equation. And when have we solved it correctly? Of course you can set your solution back into this equation and see if you have 1 equals 1. Or put everything on one side and see what the residual are. If the residual then is small enough, you should be happy. This residual can be a dangerous monitor. I mean, you can take one equation, when you write it on the form equal to 0. You can take the entire equation and multiply with 1 million. It's still the same equation. Your residuals is going to be 1 million times bigger. So what's the point? A residual really doesn't say anything by itself. But what we can do here, that is not so expensive. If we have a solution here of some accuracy, we can easily calculate the new velocities and check what's the divergence of this velocity field we have found so far. If the divergence is getting close to 0, that's something we have a physical interpretation of, because we know the divergence here should be 0. It's an incompressible flow. So there you can actually test your solution using a physical argument. That's something else. But remember, don't waste your time to go too much below this order of accuracy, because that's the error that you have in your equation initially, and you can't avoid it. Well, the only way to avoid it will actually then be using a higher order scheme, fourth order or something like that. That's possible, of course, but so don't waste too much CPU on solving it all the way down to machine accuracy. No point. Okay?
So which numbers are we comparing here? I mean, it's the divergence? Will you start with,
If possible, yes.
But-
Here we can do it, but it depends on your problem.
we know it should be the divergence should be 0, but we still got the problem of how close to 0 is
Yeah.
close enough.
So say you have a delta x of order 0.1 meters,
Yeah.
10 centimeters. Okay, then he is 1 over 100, right?
And this is the order, we don't know
No.
the prefactor here.
I know, but then you said you he's 1. I mean, you have to give him a number anyway.
Maybe it could be anything.
Well, no, it shouldn't be 10 or bigger. And it shouldn't be 0.1 or less. It should be in the order. So that's, say, the closest 10. So then I would use 1 over 100 here. And if I then find a solution with the accuracy 1 over 1,000, stop. And there's no point going further. Practical, pragmatic, and it will work. So, and it will be cheap, of course. So, and don't overdo it. That's my point. Other questions? There's been running some more cases here. And here more steps on the way up and down again. Yeah. The Pascal, you can have a look at it if you like. I think any of you know Pascal. It's a very compact way to program, and it's recursive programming, so it's really tricky to nest it up, so I won't waste too much time on it if I will. A little funny one at the end here, sort of a different way of thinking. Here we are talking a full DNS of the Navier-Stokes. And here we are talking multi-grid with the entire Navier-Stokes, not just an elliptic equation, but everything. It's a little strange, so it's actually not really multi-grid, but well, we use more than one mesh, so why not call it multi-grid? On the fine mesh here, we have 128 cells in each direction. It's a 3D case, so 2 million grid points. And this case was then run in the 80s, and in those days, when I did this simulation, I had to use the Cray 2 supercomputer. And one CPU hour costed 20,000 crowns. And now you have the same power on your laptops. And this was in the early 80s. So the world goes forward. Reynolds number 3000. That's then the flow between two parallel plates. So it's just turbulence. So the biggest Reynolds number we could handle with the DNS in those days. Remember, at DNS you have to resolve all the turbulent structures in space and time. And the problem with the DNS is that you get too much answers. You have 2 million grid points. In each grid point you have 4 unknowns, pressure and 3 velocity components. So you get a lot of data back in your face. But the problem, the flow between two parallel plates, I mean, that's the easiest geometry you can have. Set up a pressure gradient, and then you will have sort of a velocity profile, and on average, a turbulent velocity profile. Of course, the average solution, that's the one you're interested in. So you're not interested in all these numbers. You want to say one-dimensional velocity profile here would be enough. And then maybe also other quantities. We'll see more about this when we come to turbulence. But you have then to average, creating a nice smooth velocity profile, because a snapshot here will be totally chaos. So actually, the structure in the madness is not chaos. Sadly, if turbulent had been chaotic, it would be easy. But it is structures in the madness. That's what makes it hard. But that means now, to create good statistics, you need a whole bunch of solutions to the Navier-Stokes. And this is actually the way you should look at a DNS, or an LAS for that matter. It's just a whole bunch of different solutions to the Navier-Stokes. And you need many of these solutions to get good statistics, to get a good average. So you just produce a whole lot of different solutions. And actually on every time step, you have to do this in time as well. Remember, it's turbulent, and it's a DNS, you have to resolve everything in time and space. So you can't use a steady state code. That won't work. So it has to be transient. But I'm not interested in any time development here. So I'm just interested in as many solutions to the Navier-Stokes I can get. So say you have a solution on the finest mesh. And then you can create an average over all the data you have then. Then I want another solution. Then it would be stupid just to take one time step, because the time step here is very, very small. And the next time step you have very close to the previous solution anyway. They are highly correlated. So what you do, you take say 100 steps or 1,000 steps until you have a totally different solution to the Navier-Stokes, and then take an average. And that's what is quite expensive with the DNS. You have to do this many times, maybe 1,000 times, 10,000 times. The more the better. So just going from one fine level solution to the next uncorrelated fine level solution, you should just get there as fast as possible. The easy way, you just simulate. But here the idea was to get there as fast as possible. We take the solution on the fine mesh, take the snapshot, meaning take the statistics from the solution we have here, and then we push the solution on a coarse mesh, where we can take faster time steps. And the computational cost is much less. It's 1/8 of the amount of grid points, so it's much faster to get there. The time level here was called a LETOT, large eddy turnover time. So roughly the time you take to get the flow with the average velocity through the entire channel. And it would then be possible here to decrease the number of CPU hours on this expensive Cray machine substantially. So for this case, I think I spent roughly 1,000 hours altogether, 200 hours just to get the statistics up and running, and very expensive indeed. So now the idea was then to jump from a fine mesh to a coarser mesh. So you should then reduce the number of operations by a factor of 8 in 3D. Also, I could double the time step. So there you have a factor of 2 also, hence total gain, factor of 16. That should then be possible. But here, the entire Navier-Stokes was transferred. So when you are going to simulate, say after finding a fine solution here, transfer everything to a coarse mesh, then you are staying on the coarse mesh until you have simulated one entire time unit. And then you have to go back to the fine mesh. And also you had then on the fine mesh to simulate many time steps, well not that many, to sort of update this coarse mesh solution to a good fine mesh solution. So you needed some additional times that's there. So you know you didn't gain a factor of 16 totally, but you didn't have to simulate that long on the fine mesh to get a good fine mesh solution. I needed roughly 1/16 of a time unit. So definitely, yes, it was a total gain here, which was at least interesting. If you should call this multigrid, I'm not so sure. Maybe you should, well, it is too much. Also, strangely enough, here on the fine mesh, it was a DNS, meaning everything was resolved. All turbulence scales, all motion was resolved down to the Kolmogorov of microscales. Come back to that when we talk about turbulence. Now on the coarse mesh, you can't really use a DNS anymore because here the cells were too big. So here I had to switch on a large eddy simulation. So this is a DNS, but on this level I had to use a large eddy simulation, or else the solution would have blown up. And if you had gone to an even coarser mesh, then I would suggest you use K epsilon or something. Then you need a turbulence model to damp it down. That should be possible here. I didn't try it, I only used the two-level mesh, but yes, it worked. So possible. Whether one should do it or not, that is up to you. Some references here at the end. Archie Brandt, that was the guy who started it all. Well, that's not really true. He was the guy who understood what the Germans did 10 years after. The book by Briggs you have got on the material. Cute little book. All of the figures in this compendium has been stolen from him. So if you just want to learn it quick and easy, this is the book you should read. And if you really want to be nasty, then you have some very heavy books, Hackbusch, also some of Wesseling, and they are extremely complex. They go into the numerics behind multigrid. Don't do it. Way too complex. Okay, any questions? Then we take some coffee.